So let's take a look at another example here of quadrature PSK. We looked at this last time. For binary PSK, the input, we chose two phases for each symbol, right? So we had a 1 and a 0 based upon the phase. And now for PSK or quadrature PSK, and why do we say quadrature and 4 PSK? And this is something that's important, is that I'll draw it over here. In a 4 PSK, we could have one angle here, one angle here, one angle here, and one angle here. And you can see this is just 4 angles, right? So you could call this a phase shift key, or we'll learn later you can also call this a quadrature amplitude shift key, because I have an amplitude here, an amplitude here, and an amplitude here. So 4 PSK can be referred to in a couple different ways, and we'll see about that in a little bit more. But let's look at what 4 PSK would look like in our waveform. And so you can see down here, as I mentioned, each symbol, each physical state that we transmit is a collection of bits. In this case, because there's 4 states, it's 2 bits. And an important thing to understand with this is that the bandwidth of the signal is related to the time, the period of the symbol that we transmit. And so the bandwidth of the signal is related to, or the time is 1 over the bandwidth, and the bandwidth is related to 1 over the time, which will become important in just a moment. And you can see here, as I mentioned before, we're sending twice as much data. So I think a really good example to look at is in 4 PSK, I'm transmitting this signal that's 180 degrees of phase, and you get 2 bits, you get a 1, 1. In BPSK, I transmit the exact same physical signal, but it only represents 1 bit. And that's because my receiver knows that I'm traveling either QPSK or BPSK. But you can start to see how I can transmit a signal, and with higher order constellations, it's actually going to transmit more and more information. And like I said, this will become more clear as we move through higher orders. And so here's another view for quadrature PSK. We can write a 4 PSK or quadrature PSK as similar as we've done before, and now we've got 4 different phases. And we just play the same trick that we did. We're going to convert this phase into a pre-factor, and then we can just split this up mathematically. And if you're wondering, how did I go from this step to this step, you remember in class cosine of u plus v gave us a cosine of u cosine of v minus sine of u sine of v. It's just a trig identity. And then here we can just move this summation right here, and now we've got 2 signals that are right here. And if you choose these values for your phase, we know what the cosine phi of k will be and sine phi of k will be for each. And then we can actually write QPSK as this top version and this bottom version. And you can see that that's just simply a BPSK signal and a BPSK signal. And the reason we're able to do this is we basically are transmitting 2 BPSK signals, but they're orthogonal. One's cosine and one's sine. And if you remember from the analog modulation lab, we're able to transmit orthogonal signals without disrupting one another.